Hi, I'm Dean, and in the IR-OPO-OPA systems I build, there's one component that I use I call a variable wave plate. You can see it right here between the two stages, right following this dove prism mounted at 45 degrees. This is a single crystal magnesium fluoride window with the optic axis pointed normal to the surface. When you look down the optic axis, or normal to the face of this optic, you see no birefringence. You only see O-wave light coming through. As you begin to tilt this optic, you expose that optic axis and create birefringence, the amount of which depends upon the angle at which you tip the crystal. So the idler output from the OPO I'm using as a seed input to the OPO stage here. The OPO idler output is vertically polarized. Well, the needed polarization for the light coming into the OPA is horizontal polarization. So that's the purpose of this wave plate. The dove prism itself actually does give some degree of ellipticity to the beam, just due to the internal reflections that are here. But as you rotate this magnesium fluoride window from normal incidence, you first reach a point where you correct fully the birefringent or the ellipticity caused by the dove prism, and then as you continue to rotate it, you reach a point where you totally flip the idler polarization from vertical to horizontal. Now, what I do to adjust this crystal is simply look at the total energy output from the system with the power meter and optimize the angle as close to normal as possible, but at the first point where the energy is at a maximum. And that's shown at the angle right about here that you'd find at 745 nanometers. Now, to adjust this optic or to remove it, you would simply loosen the set screw and adjust it for maximum energy. Let me show you a little bit what this optic looks like. You can take it out, like I said, looking down the face or the perpendicular to the crystal, you'll be looking down the optic axis. There will be no birefringence, and so if I put two cross polarizers on either side of this, I'd see everything blanked out. But if I put two cross polarizers and then held it really close to my eye so that my eye was seeing light coming in at different angles as well, this is what I'd see. A set of colored rings with a cross in between it, showing the two polarization directions of the polarizing film that I was using. Over here I've got the magnesium fluoride angle that I find where it's a perfect half wave for these different wavelengths. And that's versus the calculated behavior for a 1 millimeter thick optic as well. Okay, now let's say you wanted to make sure that you fully rotated so that you don't have any of the orthogonal polarization in here. What you would want to do then is put the optic in so that it's at normal. We got vertical polarization coming from the idler here. This silicon stack of plates polarizer is only going to pass the idler itself, because I'm not pumping the OPA stage right now, that's blocked. And I have the silicon polarizer set to pass vertical polarization. So as you can see on the power meter right now, I have the strong signal from the idler from the OPO right now. Now if I rotate this and watch the intensity of light, I reach a point where I'm at a minimum. And that's seen on the power meter I've got here as well. This is the optimum angle that you would use for the magnesium fluoride wave plate at the particular wavelength we're at at now, 745 nanometers. So let me set the camera down. I'll just leave it loose there, actually. Normally, sticking it in just one position is good enough to cover the whole tuning range of the system, because we don't really often need to have purely polarized beams coming in. But if you do want to avoid any kind of leakage, then yes, adjusting it using something like the stack of plates polarizer to ensure that you have you're coming in with a fully horizontally polarized beam is necessary.